All right, good afternoon. I'd like to welcome everyone to the fourth and final webinar in the winter webinar series for CUAHSI. This series is entitled Urban Stormwater Hydroinformatics. I'm the host, Randy Diamond from Virginia Tech. And today's presentation is from Aditi Bhasker from Colorado State University. She's going to be joined by Krissy Hopkins from the USGS. And I'm going to turn it over to Aditi to lead off. So thank you for joining us. And thank you to Aditi and Krissy for preparing this.
Great. Well, actually, I'm Krissy, and I'm going to start us off here talking a little bit about this project that we have in Clarksburg, Maryland. So a lot of you are probably familiar with this, but just to give you sort of a very basic background about how stormwater control measures have changed over time. Over the last 50 years, stormwater management has gone through a series of transitions from no to limited stormwater control, so with stormwater going directly into storm drains through pipe networks and into streams and rivers. And then as regulations and practices have changed over time, we kind of shifted along this continuum of source control from more detention-based stormwater management, so things like detention ponds and retention ponds, these larger features that are installed on the landscape closer to the stream network to store and treat stormwater before it's released to the stream. And then more recently, there's been a move towards installing smaller scale projects like vegetated swales, bioretention, rain gardens, rain barrels, these smaller practices installed closer to the source where stormwater is generated to try to improve stormwater treatment and slow down that water before it gets to waterways. So these sort of continuum of stormwater management practices gives us an interesting opportunity to compare and contrast these different approaches to stormwater management. So what I'm going to talk about today, and Aditi is going to talk about, is a project that we've been working on looking at a case study from Clarksburg, Maryland. This is an area that's located just northwest of Washington, D.C. So you can see on the map here, the star shows approximately where Clarksburg is. And within that area, we have three study watersheds that we're going to talk about today. One is a forested reference watershed. One is and then there's two urban watersheds. One has distributed stormwater control and one has centralized stormwater management. And within this study area, the monitoring design includes USGS stream gauges, a rain gauge network, a series of groundwater wells, and also, monitoring within the stream. So some ISCO sampling with grab samples from these streams. So on the maps here, you can see the location of the stream gauge in each of the watersheds and the current land use within each of them. So within those watersheds, you can see on this map here showing the yellow circles are stormwater control measures. So the distributed stormwater management watershed has a high density of these stormwater control measures that are distributed across the landscape, typically in the uplands closer to the impervious surfaces, compared to the centralized watershed, which has more detention-based stormwater management practices located along the stream network and in some of the newer development areas within that watershed. Both of these have similar percentage of impervious cover. They're relatively similar in size. They're small watersheds, making sort of a comparison between these three watersheds a good sort of case to look at how stormwater management impacts things like water quality and stream flow. So just zooming in on the watershed with distributed stormwater management, this is what the landscape looks like. You can see the stream network, and then the different colored dots here represent the different types of stormwater control measures within the watershed. So most of them are focused on infiltrating stormwater. So there's a series of dry wells, storm drain recharge facilities, dry swales, bioswales, recharge chambers, and then some water quality focused BMPs, things like sand filters and oil and grit separators, which actually aren't shown on this map here, but they're distributed also across the watershed. And here's just some pictures of what these types of facilities look like within this watershed. So another interesting aspect of this watershed and study area is that it's very data rich. We have a lot of information from things like aerial photographs and also the county flew LiDAR data. So we have high resolution digital elevation models of this watershed showing snapshots over time as the watershed went through urbanization. So this is a series of aerial photos showing what the watershed looked like in 2002, and this is the distributed stormwater management watershed. So in 2002, it was predominantly an agricultural landscape, and then over the course of 10 years or so, the watershed was developed into suburban development. And you can see the construction phase starting in 2004, and then expanding in 2006 and 2008, and then in 2010, the watershed kind of is in its current state. And then the red areas on here show the impervious area that drains to an infiltration facility within this watershed. So if you look at the change in impervious cover over time, and this watershed went from less than 5% impervious cover to just about 30% impervious cover, whereas the other two watersheds, the forested watershed and the centralized stormwater management watershed, didn't really have any drastic changes in impervious cover over that time period. So I'm going to switch it over to Aditi now.
All right, so we're going to be talking about three different parts of focusing on this watershed and then a broader focus. So the first part is to look at the question, how do base flow and total flow change on a monthly time scale with watershed scale green infrastructure? And so with that plot that Krissy was just showing with the comparison between the distributed watershed and those other two controls, the urban centralized control and the forested control, we're going to use those controls here to compare the flow, base flow and total flow in the distributed watershed. And here what we've done is normalized by the flow, by dividing by the flow in those control watersheds. And this is to remove those climate effects and just look at what's happening in the distributed watershed relative to those control watersheds. So in the top set of graphs here are the distributed watershed flow values divided by the values in that centralized urban control watershed. And then in the bottom set of graphs here are the monthly flow values for the distributed watershed divided by the forested control watershed. And so here we've split it up into two time periods, during urbanization and after urbanization. And we've done a trend analysis on these two periods separately and to look at when there's a significant trend. And the red lines are indicating a significant trend, and the red line slope indicates that magnitude of the trend. And so on the left side here, we see these are the base flow in the distributed watershed compared to both these control watersheds. The base flow in the distributed watershed during urbanization has a significant increasing trend. Then we also see this actually a similar pattern for total flow during urbanization for both for the distributed watershed increasing in total flow during urbanization relative to both control watersheds. And so after urbanization, we don't see a consistent trend here, but it's during urbanization, we're seeing this consistent increase. The next plot I'm showing is autocorrelation of the seasonal or the monthly base flow values, and again broken up into two time periods, before 2010, which is the during urbanization time period, and then after 2010, which is after urbanization. And again, looking at these three watersheds. So on the left, we have the forested watershed, where we see the seasonal pattern in this autocorrelation plot, where we're seeing monthly base flow values 1 or 2 months apart are positively correlated to each other versus monthly base flow values 6 months apart are negatively correlated, and that's related to the strong seasonality and base flow in this forested watershed that exists both before and after 2010. In the centralized watershed, which is the urban control with centralized stormwater, we see that there's not as strong of a pattern of flow seasonality in this autocorrelation plot, either before or after 2010. We see that there's a high correlation for flow values that are close in time, but that once we get further out, there's not a clear kind of 6-month or 12-month pattern going on here. For the distributed watershed, we see before 2010, the autocorrelation plot looks more similar to the forested watershed, in that there's a seasonal pattern evident, but then we see that after 2010, this signal is damped. And so the other aspect we looked at here was recession. So looking at the falling limb for these three watersheds, and here we're showing on a log scale for both axes, the hourly flow values versus the change in hourly flow. And the two time periods during urbanization is shown in blue, and then the red dots are after urbanization. And we see that in the forested control and the centralized control, the during and after urbanization recession relationships are very similar. And we're seeing that, and down here in comparison in the distributed watershed, there's a difference we're seeing in this slope between during and after urbanization. And so we're seeing after urbanization, these recessions, the falling limb of these hydrographs is becoming more gradual, or the recession is occurring more slowly. So to link these dots together, we're seeing here an idea about a water balance on the left for pre-development hydrologic cycle, where we would, in this area, we would expect that there's most precipitation is leaving the watershed as evapotranspiration pre-development, and then there's contributions from runoff and base flow, summing up for total flow. For the case that we're looking at, as this watershed has been developed with, maybe you could say, if it didn't have this newer type of stormwater control measures or green infrastructure, a more conventional type of urban development, we would expect to lead to an increase in this runoff component, that direct runoff from impervious surfaces directly being channelized into streams. What we're seeing in this watershed is a couple of different things here. We're seeing that there's an increase in total flow in that distributed watershed relative to the control watersheds during urbanization. And without a change in precipitation, the simplest explanation for that would be that there's a decrease in evapotranspiration going on, with both a reduction in vegetative cover. So with that increase in imperviousness means there's less vegetation in the watershed than there was before. And also the other aspect that we could use as related to that is that dampening of seasonality and base flow that we saw with the autocorrelation plots. So there is this increase in total flow, likely associated with a decrease in evapotranspiration in this watershed. And we also saw, as a component of that, an increase in the base flow component of total flow. And so here, some of the kinds of facilities that are implemented in this watershed are shown to the right here. So the kinds of stormwater facilities that are been used here are really focusing that water towards recharge, focusing that stormwater towards recharge, and not necessarily providing a lot of opportunities for evapotranspiration, particularly underground facilities such as dry wells or storm drain recharge chambers that are completely underground. And so there's the potential for water that would have fallen as rain in a pre-development situation, been stored in soil moisture, and later been taken up by plants or evaporated. In this case, this water might have been more collected in a storm drain, in a storm drainage system, and channelized towards an infiltration facility and gone towards recharge, rather than what it was doing pre-development. So I'm going to talk about some of the well hydrograph data that we've collected in this watershed. So this was collected only in the distributed watershed and all post-development. And so here we are looking at recharge events. And in the bottom, this is a method developed by John Nimmo and others to look at episodic master recessions to pull out from a well hydrograph record. This is just an example from this one well, well 3 up here. So this is the water table elevation in black, and then in the blue is the cumulative precipitation, which is on this right axis. And then these dark black parts of the curve correspond to recharge events, which are automatically picked up by this code, and paired with these dark blue sections of precipitation, so that we're getting an automated way to pair recharge events with the associated storm characteristics and precipitation characteristics of that event. So on this plot on the left, we're seeing that comparison between, on the x-axis, the precipitation for every episode, every recharge episode, plotted against recharge on the y-axis for these 4 wells. And then on this box plot on the right, we're taking this ratio of the recharge to precipitation, which is being shown on the left, for each episode, seeing how much of the overall precipitation is becoming recharge, and plotting that for these 4 wells, just a box plot showing the different episodes. And so one of the things we're seeing here is that there's the spread in different storm episodes or different recharge episodes there's a spread in how much recharge is taking place out of the total amount of precipitation, and also that this well 3 in particular has a higher amount of recharge to precipitation ratio compared to the other wells. So this next slide shows some of the characteristics exploring that spread in the box plot. So what causes particular storm events to lead to greater recharge versus less recharge? So some of these are things we would expect. So this y-axis here is the recharge to precipitation ratio, the same y-axis we saw in that box plot. And then in this top left graph, we're seeing on the x-axis precipitation from that episode, that generally when we have smaller episodes, smaller storm events, we're seeing more precipitation. This top right graph is showing precipitation rates, so we're seeing less intense events were associated with greater recharge to precipitation ratios. In the bottom left, we're seeing for episode duration that longer events have larger amounts of recharge. And then this bottom right graph is showing on the x-axis the difference in the initial water table before the storm event compared to the mean. And so here we're seeing that there's, in general, that there could be a relationship. This one has more scatter, but for larger pre-event water table elevations, which means a higher water table before that event happened compared to the mean for that particular well, there's a higher recharge to precipitation ratio. So these are things that we would, in general, fit what we would expect, and here we can actually see that going on in our study watershed. So next I'll talk about why there might be a difference. You can see it in these plots too, that why there might be a difference between the behavior at these 4 watersheds, or 4 wells, sorry. So here we've plotted on the y-axis the median recharge to precipitation, considering all storm events in this watershed. And for these wells, for each well, plotting its median recharge to precipitation, and then comparing that to different characteristics of the well. So here on the first plot is the distance from that well to the stream, and the distance, then we're looking at the distance to stormwater, the nearest stormwater control measure, and then the mean depth to water. And so what we can see here is that well 3, plotted in red here, was the well that we saw had the highest recharge to precipitation ratio. So it had normalized for the same storm event, it had more recharge. We're seeing that it was different in a couple ways from the other wells. It was the furthest from a perennial stream. It was particularly close to stormwater infiltration facilities, these dry wells you can see on this bottom graph here. And it had a deeper depth to water compared to these other wells. But you can see this well 6 here is also close to dry wells, and it didn't have a particularly high recharge to precipitation ratio, but it had other characteristics which were different. Namely, that was very close to the stream, and it had a more shallow depth to water. And so really with the kind of experimental setup we have in this particular watershed, we're not able to look at specifically the effect of the distance to the stormwater control measures and the effect of that on the groundwater table behavior, because there are these other variables that are also changing in this watershed, or different between these wells. And so this is some work being carried out by a master's student Ben Schode at CSU, who's looking at virtual experiments using ParFlow for a more idealized situation to look at the effect of infiltration facility arrangement. So here we're seeing a cross-section looking at infiltration facilities spread out in this model domain, and looking at if these facilities are more clustered versus distributed, can we actually explore and model what kinds of effects that would have, varying that one kind of characteristic to isolate the effect of that one factor that we couldn't isolate in this particular field monitoring study, to look at what that does to stream flow and base flow. So with that, I will turn it to Krissy to talk about some water quality aspects.
So we also looked at sediment and nutrient export from these watersheds and how that varied over time and between the study watersheds. So I want to talk a little bit about that part of this work. So we looked at both base flow and storm flow conditions. Water samples were collected between 2004 and 2016. And if we just look at base flow nitrate concentrations over that entire time period, we can see that nitrate concentrations are elevated in all watersheds, including the forested watersheds. So all of these watersheds typically had a concentration above 1 milligram per liter. And that the concentration of nitrate was highest in the distributed watershed compared to the centralized watershed. And similar to concentrations of agricultural watersheds in the Piedmont, which can range between 3 and 8 milligrams per liter. So you might be wondering, like, well, where's all this nitrogen coming from? Why is it so high? Well, if we look back at the historical land use history in these watersheds, we can see that both the urban watersheds were previously agricultural watersheds. So back in 1960, both of them had about 70% agriculture. And even the forested watershed had about 38% agriculture back in 1960. And probably if you went back further in time, that percentage would be even higher. So this legacy of nitrogen in the soil from agriculture is still lingering in these watersheds and being flushed out. And the two urban watersheds are interesting in that they had similar amounts of agriculture previously, but sort of developed at different time periods, with the centralized watershed being converted from agriculture to suburban development in the early 80s, and then now the distributed stormwater management watershed being converted to from agriculture to suburban development in the early 2000s. So if we look at changes over time within these watersheds in terms of nitrate concentrations, you can see that in the forested watershed and in the centralized watershed, concentrations haven't really changed that much over time, but in the distributed watershed, concentrations have gone down in the surface water during base flow conditions and also in the groundwater. So groundwater concentrations are shown as the triangles in this figure. And in the groundwater, the concentrations have gone from 6 milligrams per liter to about 3 milligrams per liter today. So kind of a halving of nitrate concentrations over the course of about 10 years or so. And one of the things that might be, there's lots of factors that could be contributing to this pattern in this watershed, but some of them are related to topographic changes that have occurred within this watershed. So during development, there was massive earth moving within this watershed. So this map here is some work that Dan Jones published in Geomorphology, looking at changes. He used LiDAR data to compare a digital elevation model before development and after development to identify areas that were filled in, shown on this map here as yellow, or excavated, shown as red on this map. So you can see areas that were drastically changed in terms of the topography. And this also resulted in the removal of soils that are rich in nitrogen. It also resulted in topographic changes that rerouted flow paths that might be contributing to some of the patterns that Aditi has found in terms of base flow. And then also, because base flow has increased, that may also be increasing the sort of flushing rate of that legacy nitrogen that's stored in the soils from agriculture. If we look at base flow conditions in terms of nitrate export, we can see sort of a different pattern here. So during development within this watershed, we see a pulse of nitrate sort of shown there in the blue circle there during the post-construction phase, which loosely corresponds to this time period when sediment and erosion control facilities were converted into stormwater control measures within the watershed. So it might just be related to the timing of the conversion of these sediment controls to stormwater management. Also during this time period, there's elevated base flow. So these changes are not necessarily driven by a change in concentration, but rather a change in the amount of water within the watershed. And then we also looked at storm events. So during 2010 to 2012, a series of storm events were sampled within these three watersheds, a series of grab samples, and then also there was a turbidity sensor installed in each of the streams. So we developed a surrogate relationship between suspended sediment concentrations and turbidity to predict suspended sediment concentrations for time periods when we didn't have grab samples. And we looked at paired events. We identified events that occurred simultaneously in both the distributed stormwater management watershed and the centralized watershed. So this plot here is showing runoff in the distributed watershed and runoff from the centralized stormwater management watershed. So each of those circles represents one storm event that occurred at the same time in both of these watersheds. And because they're close together, we can make some assumptions about precipitation and antecedent conditions that were likely similar between these two watersheds to look at comparing runoff and also sediment export from these individual events. And by looking at these paired events, we can identify events where there was greater runoff and sediment export from the centralized watershed than from the distributed stormwater management watershed. And you can see that the majority of the events fall in the sort of upper left-hand corner where there was more runoff and sediment export from the centralized watershed than the distributed watershed. But as you increase in the size of that event, so the amount of runoff, the two watersheds are becoming more similar to each other, whereas they have this where they have the same, approximately the same runoff and sediment export for a given event. So this is an interesting way to try to make comparisons among these watersheds. These types of data sets are often very messy and hard to handle, and because of the proximity of these watersheds, it gives us a little bit more power to be able to compare these two events that occurred in these two watersheds while still taking into account things like antecedent conditions within the two watersheds. And then if we were to sum up all of the export that occurred during those 40 storm events that were shown on that plot before, we can look at the total amount of sediment that was exported during different types of events. So here's just a bar plot showing the total amount of sediment exported and also what proportion of that sediment occurred during a small versus large event. And we can see that the distributed stormwater management watershed had less export of sediment overall compared to the centralized watershed, but the majority of the export occurred during those large storm events. So it just gives us a way to think about, what types of events are we able to characterize in terms of monitoring, and what is the impact of those different event sizes on overall export. And also, if you're thinking about managing for different size events, if you're managing for an inch of rain versus 2 inches of rain, that design criteria can influence, how much storage you have within those stormwater management facilities to reduce the volume of water that's eventually sent to the stream. So I'm going to switch back to Aditi, and she's going to try to wrap up and kind of give a sort of larger summary of how, to think about these types of factors influencing hydrology and also water quality.
All right, so our third section question is, how would we expect flow and water quality to change with different types of stormwater control measures? And so this is coming out of work that was led by Ann Jefferson, a synthesis effort to look at existing monitoring and modeling studies that have looked at watershed-scale implementations of stormwater control measures. And from this, we developed some hypothesized relationships of how we would expect different types of stormwater control measures to affect flow and water quality. And so the reason I'm saying they're hypothesized is that they're based on those studies that we do have, but in particular, they're for monitoring studies for observed changes with watershed scale implementation of stormwater control measures, and studies really documenting and monitoring with the hydroinformatics kind of approach, looking at that transition. Those are relatively rare, and we don't have necessarily a lot of those. But so these are based on those existing studies, but also hypotheses that we're suggesting could be further tested to see how this would perform in other watersheds. So what we're showing here is on the x-axis is untreated impervious cover increasing. So as we're developing, and in particular this unmanaged stormwater curve, as we're developing with more impervious cover that's not treated by stormwater control measures, so that's what unmanaged means here. This on the x-axis here, the 2-year peak discharge we would expect to increase, maybe increase more in a critical zone of impervious cover, and maybe less sensitive at the edges. But in general, increasing peak discharge. And then here in purple is what once we're starting to implement stormwater control measures, we're now going backwards on that x-axis. So we still have impervious cover, but now we're treating that with stormwater control measures. So we're moving to the left on the x-axis, but at first we might expect that the effect of those stormwater control measures might not be detectable immediately if only a small fraction of the impervious cover is being treated, and the overall watershed might not be able to be detected on a watershed scale looking at overall flow. And so at first we're moving backwards on the x-axis, but we're not changing the peak discharge. But then as we're treating more and more of that impervious cover with stormwater control measures, and in this case, we're thinking all of the stormwater control measures will behave similarly, then we're getting this reduction in peak discharge. And the way we were expecting this to occur is that this return curve for the stormwater control measures might not be the same as when our original development was happening, and we might not return, even if we're treating all the impervious cover in the watershed with stormwater control measures, we might not return exactly to where we started in a pre-development condition. And some reasons for that might be that these stormwater control measures have some kind of storage volume, and when that storage volume is exceeded, so there might be bypasses or overflows, and so just the raw measure of treating the impervious cover with stormwater control measures doesn't necessarily mean all the effects of that impervious cover are completely removed. So the next plot shows a similar type of idea in terms of the x-axis has untreated impervious cover, and then on the y-axis this time we have lag time from rain, the precipitation event, to the flow event, and we're seeing the unmanaged stormwater we would expect as we're getting more untreated impervious cover. We're having a shorter lag time from that rain event to flow. And then again in purple, we're starting to treat that impervious surface cover with stormwater control measures, and the effects of that might not be initially detectable. Once we do have enough stormwater control measures so that the effect is detectable, in this case, we were expecting that this effect on lag time would be different based on what type of stormwater control measure is being used. So for example, the stormwater infiltration line here would increase our lag time the most out of these types of stormwater control measures, because we're putting that stormwater into some much longer flow paths with longer travel times through the groundwater subsurface system, compared to, for example, on the other end is stormwater harvest, where we're actually removing that water from the stream altogether through either evapotranspiration or indoor use, and so this is not going to be affecting the lag time much. Then the next plot is showing water yield on the y-axis. Again, we're seeing this unmanaged stormwater curve along with untreated impervious cover. We're expecting an increase in water yield overall. And then again, there might be some implementation of stormwater control measures that we don't detect on a watershed scale. But then once those effects are detectable, here there might again be a split depending on type of stormwater control measure. So in this case, stormwater harvest is removing that water completely from the stream, and so might have the largest effect on water yield, bringing us closest to our pre-development conditions, versus stormwater detention up here at the top might have some reduction in water yield through evaporation or infiltration, but the detention facilities aren't necessarily geared or built to target that water yield reduction. So there might be a relatively small effect, and the stormwater infiltration we are thinking might be in the middle of that, in between those other two types. So the base flow discharge one is a little messy looking, because we're having, just to focus on this unmanaged stormwater curve in the beginning, as we're going to greater amounts of impervious cover, there could be situations where we would observe base flow increasing or decreasing with increasing impervious cover. And then from that point, wherever that built out point is and the base flow at that built out point, we would expect these types of stormwater control measures to act in similar ways. So the stormwater infiltration would increase base flow discharge from wherever that starting point is. And in this case, where the base flow is lower than the pre-development condition, depending on the amount of stormwater infiltration, we might be still below pre-development, at pre-development, or even above pre-development conditions. The stormwater detention keeps base flow relatively similar, versus the stormwater harvest might decrease base flow potentially for moving that water from the stream. And then next, Krissy's going to talk about the hypotheses for water quality.
So yeah, then we also thought about, how could these sort of patterns influence water quality, including the particulate and dissolved portion of say, nitrogen or phosphorus, for example. So these sort of patterns here follow a similar pattern to the sort of peak discharge that Aditi showed before, where mass generally kind of follows water with a decrease in loads as more water and runoff is retained through stormwater control measures. And then sort of the starting point for the mass shown here in the gray sort of dotted line there reflects some kind of legacy or system memory within the watershed. So something like agricultural history, for example, that might influence that kind of starting point of where that brown line starts. And then as more stormwater control measures are put into the landscape, once you reach a certain amount or density of these practices, you would see a decline in the export of the particulate and dissolved loads with more of a decrease in that particulate load, but still not quite getting back to that initial condition in the watershed. And then the shape of this curve would depend on things like processes within the stormwater control measures, so how they were designed and function, things like maintenance, the size of storm events, and also antecedent conditions. So this provides a way to kind of think about, how would installing these stormwater control measures in sort of different densities across the landscape influence mass export and also vent mean concentrations within the watershed itself. And then what are we expecting to get back to? Can we even get back to the sort of natural state before urban development occurred? And then on the next slide, this literature review, we also looked at the types of and variety of metrics that monitoring studies are using to look at water quality and hydrology, and we found a wide range of different types of metrics. So this is showing different hydrologic metrics that have been used to evaluate watershed-scale stormwater control measures. So most of the studies look at peak flow or this other category, which includes a range of different metrics or flow volumes. Fewer look at things like evapotranspiration and recharge, groundwater, changes to groundwater table. So this is kind of a limitation of some of the types of studies that we've done where, we might do, a case study in one area, but it's very hard to make comparisons across watersheds when we aren't using standardized metrics. And maybe this is a situation where something like Hydroinformatics can help us think about how to look at how these different control measures function across different landscapes and climate regions. If we can use more sort of new sensor technology and develop more open source tools that allow us to have a more standardized way to process and analyze these types of data sets, maybe we can start to sort of test and tease apart some of these hypotheses that we sort of outlined in this review paper. And the types of study designs that might be sort of well suited for this type of analysis, are things where you would measure the same metric across watersheds with different types of stormwater control measures, or watersheds in different environments that have the same type of stormwater control measure. Another case where you might be able to sort of look at these patterns is retrofit installations where you have sort of a pre-development condition before the stormwater control measure went in, and then afterwards, and maybe you had a watershed with a certain type of retrofit in one scenario and a more advanced type of retrofit in another scenario. So this is an area that we think there's a lot of potential for future research to look at how, what density of stormwater control measure do you actually need to shift this mass export towards the lower end towards the pre-development condition. And just to summarize and kind of wrap up everything that we talked about, and I guess we'll have about 10 minutes for questions. From this study in Clarksburg, we see that urban base flow and total stream flow have increased during development in this watershed with green infrastructure, and that these stormwater control measures are able to reduce runoff volumes and sediment export compared to centralized management, especially for small storm events, and that these shifts in the flow regime and water quality with different types of stormwater management, we have these general sort of hypotheses of what we expect might happen, but this requires further testing to see if these patterns hold up in the real world. So I think that's it, and we can take some questions, and thanks for everyone for calling in.
All right, if you have any questions, please type it into the chat and questions box, and we'll read it out loud for Krissy and Aditi to answer. So we'll give it a few minutes for people to type in their questions. Well, Ann Jefferson says, great job, Aditi and Krissy.
Thanks, Ann. We're glad you could call in. And yeah, feel free to email us if you have any questions or want copies of any of the papers that we presented the results of today.
We have our first question from Chris Harrington. His question is, what about the differential maintenance requirements and probability and consequence of SCM failure between the centralized versus distributed scenarios?
That's a great question about maintenance. So we didn't specifically focus on maintenance or have information about how often things like retention ponds within the centralized watershed or, sand filters within the distributed watershed were maintained. So that would be something that, we could look at in the future, but we didn't have that information compiled in a way that we could use it in this study. So I guess that's one of the limitations of trying to think about maintenance is it's hard to find a centralized location where that type of information is kept, or find out who knows, about that information. But that maintenance could also impact the shapes of those curves also. So you could think about how maintenance might influence this hysteresis idea that we talked about for different types of BMPs or stormwater measures. I don't know if you have any thoughts, Aditi?
Well, and that might also be a reason, if we were able to get at maintenance records, that might be a reason to track some of these changes. We were looking at changes with treating more impervious cover, but there may be changes just related to degradation over time with if maintenance is not being kept up. So even at the same level of stormwater control measure treatment, there could be changes in performance over time related to maintenance issues. So other things that, I would say could be tracked and studied as another axis of change here.
All right, there's a comment from Steve Burgess. His comment is, there is need to consider measures that meet NPDES stream discharge standards. Also need to consider the change in latent and sensible heat patterns in space and time. There is also need to assess overall stream health. One measure is benthic index of biologic integrity.
Yeah, so we do have some information about stream health in these watersheds, and we didn't. Do we have a slide on that, Aditi, at the end maybe? I don't know. But, in general, I think there was, okay, so here's stream IBI scores for these three watersheds. Sorry, it's in black and white. It's kind of hard to see, but The forested watershed is the triangles in this figure showing, relatively good stream health. And then if you look at the squares there, that's the distributed stormwater management watershed, which, in general had relatively good stream IBI scores up until about 2005, and then it's kind of declined since then. So that corresponds with the time period of when development occurred in this watershed. But we're kind of looking at so this graph here only goes to 2010, but the county has collected additional data up until last year. So we're looking at, okay, well, if the IBI scores have gone down in this watershed since 2010, but has there been some kind of rebound or recovery period after development? So, you could look at trying to link changes in hydrology and water quality to something like the IBI score, but it's a very complicated story to try to tease apart. But we're lucky that we do have these reference watersheds, including the forested one and the urban watershed, which is with centralized stormwater management, which is crystal rock labeled on this figure.
And the other comment about the latent heat, the energy fluxes, we didn't have any specific information on that on these sites. And I think, that component is important to think about. And I'm thinking about it from the perspective now being in Colorado in a semi-arid system, and where the water use component of this green infrastructure and could be an important component or service or disservice to really try to quantify. And I think the first part was about NIPD's flow components.
Discharge standards, I think, is what the comment was about. Yeah.
Yeah, and so that would be one of the obvious kind of metrics to use for comparison across sites, to look at how different types of stormwater control measures on a watershed scale are performing.
Okay, we have a few other questions. One from Rona Donahue, I think, refers back to the previous question from Chris Harrington. It says, were any other water quality parameters besides N affected by SCM?
We really only looked at nitrate for the most part. We had some data on phosphorus, but there really weren't any sort of big changes within the watershed, and we had less data for phosphorus. So yeah, mostly we just looked at sediment and nitrogen. I think there's a little bit of additional information from groundwater that the county collected, but in terms of data that USGS collected, it was only nutrients and sediment.
Okay, the next question is from Stephen Kramer. Is geomorphology a factor in BMP locations? I noticed that well 3 had increased effective recharge and was located in alluvial fan deposits.
Yeah, so that well was located in this valley that was this kind of an ephemeral stream situation there. And so we didn't have, there was, the aspect of its position in terms of it was in a kind of different topographic setting. And also we didn't have, we had information on that. We didn't have information on subsurface property differences between the locations and kind of specifically for that well in comparison to the others, but we were looking at how the position of that well, because it was in this valley that was downgrading of these dry wells, but also it was not directly next to a stream. It didn't have that kind of water table elevation constraint of being right next to a stream, and so could be one reason it could fluctuate more dramatically in terms of its water table elevation.
Okay, next question is from Charlie Stillwell. Do you think percentage of impervious treated is an appropriate metric to measure level of GI implementation? Treatment from retention varies greatly from swales, bioretention, etc., which might explain the hystereses. Any other ideas for alternative metrics?
It's not the best. It's maybe not the ideal one, but we could not, I guess, integrate all the different types of levels of treatment and areas of treatment into one easily measurable kind of quantity. And so that's what we were using, knowing that the just treating an impervious surface, that can have a lot of different meanings and levels depending on what type of facility is in place there. So in terms of being a cause for the hysteresis, I guess if you're able to have a measure which is measuring how effectively that stormwater control measure is able to completely remove the effect of the imperviousness and bring you back to pre-development conditions, then you're able to completely do that, then you might not have that hysteretical behavior. But we weren't thinking that would be a common situation.
All right, last question is from Ethan Yang. Do you have any information regarding the social acceptability of these distributed stormwater practices? I mean, how the neighborhood feels if they have, for example, a rain garden in their community?
Yeah, so this project didn't consider the social side of stormwater management at all. All of these stormwater control measures were either, in the sort of right-of-way area in front of the houses or behind the houses. Some of the downspouts were connected to these recharge chambers, but this was a new development, so the people who purchased those houses, that house, knew that was the type of stormwater management facility that was part of their house now. So we didn't really look at how people felt about these different facilities or how they use them, other than anecdotally just seeing people outside and asking them about them. So we didn't really look at the social aspect of this at all.
Yeah, we didn't study how people felt about their stormwater control measures that are around them, but one of the reasons why this particular watershed had this regulation put into place to use this newer kind of stormwater management in the first place is partially because of community groups in the area really mobilizing and pressuring the county to preserve their what they felt like were their water resources in that area and the aquatic ecology of the area that they felt would be disrupted with this new development. So there was opposition to the new development being proposed, and so through that, more strict regulations were put into place.
Okay, well, that's all the time that we have. Just wanted to thank Randy for hosting this winter Cyberseminar series and all the speakers, including Aditi and Krissy, for taking the time out of their busy schedules to present on their research. So thank you, everyone, for attending. And then please stay tuned. We do have a spring Cyberseminar series coming up, and we'll be making an announcement about that series in the next couple of weeks. So thank you, everyone, for attending, and have a great day.